All right, so now on this graph, okay, I want you to think not as the x-axis as being theta, as being an angle. I want you to think about the x-axis as being a distance. So what does this function become if the x-axis is distance, horizontal distance, and the y-axis is the height? Okay, so this is going to be a little bit different. Let's write a function for that, and let's graph that one as well.
All right, so here is the sketch for the last drawing, okay, where we did the x-axis actually as theta, as a theta axis with radians, and this is height. But what are we changing this now to? We're changing this to be some distance x, which we will have to measure in inches. Now, our period is no longer 2 pi, right? It's not that it repeats every 2 pi inches. That was for the angle. So we've got to reset up this x-axis. Now, before we get to that, let's just confirm this. Is it still going to start at 25? Okay, if we start at the top, yeah. Is it still going to drop all the way down to 3 inches off the ground when it's at the bottom? Yes. Is it going to oscillate above and below 14 inches? The answer to that is yes. So really the thing that we have to change here is just our units here, which on the x-axis, which means we have to change the period. So what is the period now? How long, how far is it from there to back where we started? Well, take and picture our wheel, and it is rolling. Okay, it's going to spin here. It's going to roll. What horizontal distance will it have to travel before it's back to where it starts? Well, we know it's going to be back to where it starts when the circle does 1 full revolution. And how far does this point travel when we do 1 full revolution? How far does the wheel go in 1 full revolution? Well, it goes the circumference of our circle. So what is the circumference of our circle? Okay. Well, the wheel, okay, now we have to go, because it travels along the outside of the wheel, so the true distance is the circumference of the outside of the wheel, not the thingamajigger there. So our circumference is going to be what? What's the diameter of our wheel here? 28 inches. So our circumference is 28 pi. Okay? And that's got to be our new period, doesn't it? Doesn't our period have to be 28 pi? Okay? We've got to end here at 28 pi. When it's traveled a total distance of 28 pi, now it's back to where it started. Okay? Now, if we have a different period other than 2 pi, we know that's going to change this. So how do we find that? Okay? Well, we know that the period is 2 pi over, usually we write absolute value of b, but we're not doing anything with reflection, so it's 2 pi over b. So we're going to set 28 pi equal to 2 pi over b. Well, that's 2 pi divided by 28 pi. b is 2 pi over 28 pi, so b is just 1/14. So we're going to have to change this to be a 1/14 x. We still have our plus 14 to slide the midline up. Let's take a look at that graph. Here it is. All right, let's adjust this. Now I'm going to call this h of x, and we're going to put a 1/14 x in there. Let's get the plus 14 out. Okay, so this is what we have. Let's see what this looks like. It starts 25 inches above the ground. At 14 pi, it is now 3 inches above the ground, and at 28 pi, it's back to 25 inches of the ground, above the ground. So, is this what it looks like? We've got a function here. We identified the period correctly here at 28 pi, but is this really what this would look like? Interesting.
All right, so what's it really look like to follow the path on a point on a wheel as it travels down the road? So what I have here
is a circle, and I have put a hole in it so that I can take my marker and I can put it in there and we can spin it and see what happens. Now, take a look at that. Does this really look like a cosine or a sine function? I want you to look in particular right here. We know that when we look at graphs of sine and cosine that they nice evenly go above and below that midline here, but we can see something a little bit sharper happening right there, can't we? Okay, so we got something a little bit different going on. In fact, if we look at where I placed that hole, okay, it was just in a couple inches from the outside of the wheel. What would it look like if I actually traced a point on the edge of the wheel? And now it's not going to be perfect because I'm running over the marker here and I've got to the edge here. So we're just going to pick that up right here and we're going to go this way. Now, look at that. It's kind of like that V shape, almost like how you draw a bird, you know, flying in the sky on a quick sketch here. What we actually have here is called a cycloid. So I think we should look at this a little bit more. All right, so to help us guide us through this here, I'm going to have to remind you about something I looked at a little bit briefly with you guys back in quadratics, and that's called parametric equations. Because what's happening as that point on the wheel is spinning, and that wheel is going down the road, both the x-coordinate and the y-coordinate of that point are changing. So we're going to use parametric equations to look at this. And let me remind you how they work here. Let's go into Desmos. Okay. Now, we put in parametric equations with by putting them in as an ordered pair, and we have to use a third variable. So we're going to have x comma y, but x and y are both dependent on some third variable. In Desmos, I really like to use t. I don't think theta works, so we're going to use t. So I could do something like t comma t squared. Okay, that's a parametric equation. It's a rather simple one. Okay, the x-coordinate is t, and the y-coordinate is at t squared. Now I'm graphing this from t's from 0 to 1. Let's just go maybe 0 to 4 here. Okay. And let's think about that. Well, when t is 1, what are the coordinates of our point? 1 comma 2. Excuse me, 1 comma 1. Okay, it's right there. Now in Desmos, you can't trace the parametric curve just because of all that's going on. But if we put in 1, we get 1 comma 1. If we put in 2, we get 2 comma 4. Notice this is our same old just y equals x squared equation. If I just graphed from like -4 to -4, there's our classic parabola. It just stops on either end. But you can do other things with this. You could, let's go back to 0 here. If I put it in a 1/2 t for my x-coordinate, now when t is 1, our point would be 1/2 comma 1. Okay, 1/2 comma 1. And if it was 2, it would be 1 comma 4. What we've done is we've horizontally compressed it. And we can do things a lot more interesting than parabolas or lines. I mean, we could do something like an e to the t. Whoa, look at this graph now. This is getting really interesting. Okay. If we put in a point, put in 0. E to the 0 is 1. Or excuse me, let's put in 1. E to the first is e. 1 squared is 1, so our first point is e comma 1, which would be, go back in here, e is about 2.78. It's right about there. So we can get some really interesting curves. Now let's get back to our trig. Well, kind of our favorite thing is that unit circle, right? And how does that unit circle? You wrote this exact same thing, except instead of t's, you had theta on your unit circle. The cosine of t comma the sine of t. Isn't the x-coordinate the cosine of the angle and the y-coordinate the sine of the angle? And we can graph this from 0 to 2 pi, and there's our full unit circle. Okay. Now what would happen if I made this a 2 and this a 2? Okay. Now it's our unit circle with a radius 2. We were just multiplying it by 2, but did you notice when it was like that? Now it's an ellipse, isn't it? Okay. This is 2 times the cosine of the angle for the x-coordinate, and the y-coordinate is just the sine of the angle. So you can do really interesting things. Now let's get back to our wheel problem. Okay. And let's see if we can't work through this. Now let's start a little more simply, and pen's not working. Let me pause this here for a second. All right, my pen's working now. So to make it a little bit simpler here to start with, let's just pick a point at just on the very outer edge of the circle. So let's say we start right there. And on each of these circles here, it's the wheel spinning. I'm just like taking a snapshot at different angles of rotation and then put them all together so we can see what happens. It's really important to track the center of the circle and our point on it. Now let's stick with that radius of 14 for our wheel. Okay, and what are the coordinates of this point? 0, 28. Pretty simple to start with. Now what's going to happen is this wheel is going to start to roll, and it's going to travel from there to here. Now as it's rotating, as it's rolling, it's coming there, and this point ends up right there. Now the y-coordinate of that point is pretty simple. That's just 14. But what is the x-coordinate? So what we have to consider here is we started at x-coordinate of 0. We're ending up here. How far did the wheel travel while we did that rotation? What is the distance from there to there? Well, I stopped right here at an angle of pi over 2. So just like if the wheel does a full revolution, it travels a distance equal to its circumference. Now it's done a fourth of a revolution, so it's going to travel a distance a fourth of the circumference. It's going to travel a distance equal to that arc length L. Now how do we find arc length? We know arc length is just, we didn't use L in this class, we used S, don't we? Okay. S, the arc length, equals r theta. So in this one, our radius is 14 and our angle is pi over 2. So that gives us 7 pi for the distance it traveled. So from there to there is 7 pi. Now, this point is not at the center of the circle. It's added on another, how far is that? 14. So the x-coordinate of that point is going to be 7 pi plus 14. Y-coordinate, 14. Now what do we have to do? Well, now we need to rotate again. And let's rotate another distance of pi over 2. So from there to there was pi over 2. Now we're going to go another pi over 2. We're going to be at an angle of pi. There's the center, and now we're down here. Y-coordinate is simple. It's 0. What is the x-coordinate? Well, how far did it travel from there to there? Well, we went another fourth of the circumference here, didn't we? Okay, we went another 7 pi. So the x-coordinate here is a 7 pi and another 7 pi, which is 14 pi. Now in the last one, we had to add a plus 14 because it was actually to the right of the center of the wheel. That's not the case now. Okay. It's just lined up right with it. So that's just 14 pi, and the y-coordinate is 0. Now let's do another rotation. Now we're over here. We've done a total of 3 pi over 2. Okay. Y-coordinate is going to be back at 14. What's the x-coordinate? Well, we've traveled from the center of the wheel to the center of the wheel, another 7 pi. So this is at, right there, what are we at a total? We're at a total of 21 pi. But now we got to subtract off that distance, and we have to subtract 14. Now when we're at 2 pi, we're back up to the top. We've traveled another 7 pi. So the x-coordinate is going to be at 28 pi. Notice it's lined up with the center of the wheel here. And we are at 28. And that makes sense. Didn't we say that 1 revolution, so 2 pi radians, is going to travel a distance equal to the circumference of the circle? So we're going from 0 out to 28 pi. So now how do we put this into the parametric equation here? And coming up with the equation for the x-coordinate is the difficult one. But hopefully with what we've laid out here, we can figure it out. Notice what's the same here. 0, 7 pi. I didn't write this in. That's 14 pi. This was 21 pi, and this is 28 pi. As we follow the center of the circle, we're counting by 7 pi's, aren't we? But then we have this, well, we got to add 14. Here we got to subtract 14. You know, here we're adding 0 or subtracting 0. How do we do that? Let's think about this a little bit more. Well, it seems that we have our multiples of 7 pi. And how did we get that multiples of 7 pi? We took r times theta. So that the x-coordinate is always going to be the radius, 14, times theta. Now it ended up being multiples of 7 pi because I went by rotations of pi over 2. If we did different rotations, it would be different. But our arc length that it's traveled is just r theta. So that's 14 theta. But then we have to add on or subtract on something. Now notice here, when we're at 0, we added 0 to the x-coordinate. When we were at 7 pi, we added 14. 14 pi, we added 0. 21 pi, we subtracted 14. So it's like 14, 0, negative 14, 0, 14, 0, negative 14, 0, and so on. That should remind you, if I said 0, 1, 0, negative 1, that should remind you of the sine function. We're just going to stretch that out. Instead of adding 0, 1, negative 1, 0, we're just multiplying that by 14. We end up with 14 sines of theta. Let's check that out. Let's pick an angle. Let's pick pi over 2. 14 times pi over 2, 7 pi. What is the sine of pi over 2? 1. 14 times 1 is 14, so we have 7 pi plus 14. Let's try it at pi. Well, 14 pi, got that. 14 times the sine of pi is 0, so it's just 14 pi. How about at 3 pi over 2? 14 times 3 pi over 2 is 21 pi. The sine of 3 pi over 2 would be negative 1, so 14 times negative 1 is a minus 14. Out here again at 2 pi, that's 28 pi. The sine of 2 pi is 0, so that term is gone, and it works out. We've got that x-coordinate. Okay. Now, how about the y-coordinate? Well, let's just think about this here. Our y-coordinate is our height. So we need to figure out our height in terms of the angle. And haven't we already did that in this problem? Let me go back. Here it is right here. Here I asked you to write an equation for the height given the angle theta. That hasn't changed. Okay. Now here it was 11 because we were doing the thingamajigger, not the edge of the circle, but it's 14 cosine of theta plus 14. Okay, let's graph this. All right, so our x-coordinate was, what was it? 14 theta, I'll use t, 14t plus 14 sine of t. Let me just double check that I got that right. Yep. And the y-coordinate is 14 cosine of t plus 14. Look at that. And that looks exactly like what I did on the board over there, doesn't it? Okay. Let's just make sure that our points are good. Let's pick our last point. Now I said let's show from 0 to 2 pi. We know at 2 pi, what should our coordinates be? Our coordinates should be 28 pi, comma, 28. Right? 28 pi, comma, 28. And there it is. Whoops. There it is right there. Okay? And it matches up beautifully. Now it's really fun when you watch it go way out there and you watch that bicycle, that point on that wheel and that bicycle just go and go and go. It's like it's bouncing. It's a really cool effect. All right, I think this video is getting plenty long. I'm going to stop it right here. We'll continue with the next part in the next video.